Hello everyone and welcome to A+ Physics. I'm Dan Fullerton, and in this video we're going to take the AP Physics C Mechanics free response exam from 2016 and see what we can do with it. Now as we go through these solutions, please take note that the official scoring guide from the College Board has not yet been released. That means it's quite probable I make a small mistake or two, but hopefully this gives you a feel for the questions at least. So with that, let's start with mechanics problem number 1. Pretty straightforward. They've got a cart with a force sensor and a string and a motion sensor all on the same plane. They ask us on the dot below, which represents the cart, draw and label the forces, not the components, that act on the cart. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So the way I would do that is I would start off with my dot. And the forces that I see on it, well, we've got the normal force pointing up, balanced by the gravitational force, mg down. We've got the force of tension from the string, and of course, we've got some force of friction opposing that motion. So I think that would get you through part A. Then on B, it says on the grid below, plot data points for the acceleration of the cart as a function of the force sensor reading. Clearly label all axes. Draw a straight line that best represents the data. Okay, so really all we're doing is plotting points and filling in the line. Should be pretty straightforward. I'll do that right over here. So that's pretty much what my graph looks like right there. Then using the straight line from the graph, calculate the mass of the cart. Well, for part B2 then, using that, I would say that slope is rise over run, which is going to be our change in acceleration over our change in force, which implies then, since F equals ma, Newton's second law, acceleration over force must be 1 over mass. Now if I take a couple points on my graph, and I've circled them there so you can see which points I'm using to find the slope, I get 0.8 meters per second squared minus 0.06 meters per second squared divided by our change in force, which is 0.66 newtons minus 0.3 newtons, comes out to be about 0.74 meters per second squared divided by 0.36 newtons, which implies then that the slope is equal to 2.06 meters per second squared per newton, which is 2.06, 1 over kilograms. And if the mass is 1 over the slope, this implies then that the mass is equal to 1 over the slope, or 1 over 2.06, 1 over kilograms, which comes out to be about 0.49 kilograms. So that would answer B2 for me. And then 3, using the straight line from the graph, determine the magnitude of the force of friction. Well, as I look at that part for B3, what I would look at that as the force, as you look at that graph, that must be the x-intercept, where the line crosses the x-axis. So the force of friction is our x-intercept, which occurs at right around 0.27 newtons, according to the way I plotted the points and drew my best fit line. So I think that would take you through part B. Now let's move on to part C. The experiment is repeated using a constant force sensor reading of 0.45 newtons. The cart starts from rest at time t equals 0 and is pulled for a time of 2 seconds along the track. Find the acceleration of the cart. All right, well, I would use Newton's second law and apply it, that the net force in the x direction is going to be the force of tension minus the force of friction, right from our free body diagram previously, which is 0.45 newtons minus 0.27 newtons, which comes out to be about 0.18 newtons, and that must be equal to our mass times our acceleration. Therefore, our acceleration must be 0.18 newtons divided by our mass, which we figured out previously was 0.49 kilograms. 0.18 newtons over 0.49 kilograms is 0.37 meters per second squared. So I think that would cover us for C1. C2 says, oh no, the string breaks at time t equals 2 seconds. Calculate the time it takes for the cart to stop after the string breaks. Well, that then becomes a kinematics problem. At t equals 2 seconds, the velocity of the cart is a times t. So at t equals 2 seconds, velocity of cart is just going to be a times t, which is 0.37 meters per second squared, our acceleration, times 2 seconds, or 0.74 meters per second. That's going to be its starting velocity, and its final velocity is going to be 0. So we could write v initial for this part of the problem, as we're looking at the time after the string breaks. V initial, 0.74 meters per second. V final must be 0, it's coming to a halt. And our acceleration is our net force divided by our mass, where our net force now is just our negative 0.27 newtons, our frictional force divided by our 0.49 kilograms, or negative 0.55 meters per second squared. I can then use the kinematic equation. Final velocity is initial velocity plus acceleration times time. This works because we have a constant acceleration with a constant force. Therefore, the time it takes must be v final minus v initial over our acceleration, or 0 minus v initial, 0.74 meters per second, over acceleration of negative 0.55 meters per second squared. And I come up with a time of 1.34 seconds. So I think that covers us for C2. Now we get to part D. The experiment and analysis in A and B are repeated with the cart that has the same mass but a greater force of friction. Will the slope of the new line be greater than, less than, or equal to the slope of the line in part B1? So for D1, I'd say we're going to have the same slope. Remember, the slope of the line gives us our mass. Mass isn't changing, so we have to have the same slope, because our slope was 1 over the mass. So I would put that in a sentence. In D2, will the horizontal intercept of your new line be greater than, less than, or equal to the horizontal intercept of your line in part B1? Well, that's going to be greater than. The x-intercept is the force of friction, so if the force of friction is increasing, the x-intercept must also increase. So I think that covers us for question 1. Pretty straightforward for an APC mechanics exam. All right, let's take a quick break and we'll come back with question number 2. All right, and we're back with question number 2. Here we have a block of mass 2m on a horizontal frictionless table attached to a relaxed spring as shown. The spring is nonlinear and its force is given by negative bx cubed, where b is a positive constant and x is its displacement. We also got a block of mass 3m and initial speed v0 moving to the left. Then it says on the dots, draw the forces before they collide. So the block of mass 2m, if I were to draw its free body diagram, we have a normal force on it, and we have 2mg, its weight down. For the block of mass 3m over on the right, we'll start with our dot again. We've got the normal force on it again, and I probably ought to draw that a little bit more to scale. Since we know the weight must be 3mg, I should probably make that a little bit bigger, and the normal force the same size, pointing upwards. And I think that covers you for the free body diagrams. Now for B, it says, derive an expression for the speed of the blocks immediately after the collision, when they collide and stick to each other. And that looks like a conservation of momentum problem from my perspective. So for part B, I would look at the initial momentum must equal the final momentum. Therefore, the block of 3m starts with speed v0. The block of 2m starts with speed 0. So there's our initial momentum. And after the collision, the two stick together. They act almost like they're one object, 3m plus 2m times v. Which implies then, on the left-hand side, we have 3m v0 equals 5mv. Therefore, v equals 3m v0 over 5m. Therefore, v equals 3/5 of v0, or v initial. So that covers us for part B. Again, another fairly straightforward problem. For part C, We're now asked, determine an expression for the kinetic energy of the two-block system immediately after the collision. Again, it looks like another straightforward question. The kinetic energy is 1/2 mv squared, which is going to be 1/2 times our mass, 5m when they're stuck together, times their speed, 3/5 v naught squared, which is going to be 5m over 2 times 9 v naught squared over 25, which looks to me like that's going to work out to be about 9/10 mv naught squared. And D, derive an expression for the maximum distance, capital D, that the spring is compressed. All right, now we're getting to a little bit more sea-level questions here. I would use the work-energy theorem here, where the work is going to be the change in the kinetic energy of the object, which is the integral of f dot dx. This implies then that our kinetic energy, our change of 9/10 mv naught squared, must equal the opposite of the integral as we go from 0 to capital D of minus our force, minus bx cubed, times our dx, where the negative comes in from the fact we've got our force and our displacement in those directions. Which implies then that 9/10 capital M v naught squared must equal, we can pull the negative b out of the integral sign. We've got negative b, that's going to be a positive, and we have x cubed, the integral of x cubed with respect to x is going to be x to the 4th over 4, in our limits of integration from 0 to d. This implies then that 9/10 capital M v naught squared must equal capital B d to the 4th over 4. Little bit of algebraic manipulation here. 9/10 capital M v naught squared equals b over 4 d to the 4th, which implies then that d to the 4th must equal, we have there 36 over 10 capital M v naught squared, which implies then that capital D, when we take the 4th root of this, must be 18 over 5, oops, this was 10b there, my apologies, over 5b capital M v naught squared, all raised to the 1/4. And I'd probably leave it there. You could simplify further, but I think that'll get the point across just fine. Okay, now we've got part E. In which direction is the net force, if any, on the block of mass 2m when the spring is at maximum compression? Well, at maximum compression, that must be to the right. The displacement x is negative, so force, which is minus bx cubed, is positive to the right. Also, the block is accelerating to the right, so the net force, or the force of the spring, must be to the right. So you would answer that in a sentence or two. And F, do the two blocks, which remain stuck together and attached to the spring, exhibit simple harmonic motion after the collision? Well, no, absolutely not. Simple harmonic motion requires a linear restoring force, a force similar to the pattern F equals minus kx. This is a nonlinear spring, negative bx cubed, so it's not going to exhibit simple harmonic motion. And that answers question 2. We'll come back in just a moment with question 3. So what they give us is that diagram, which you can see, which we have a rotating table. We've got a spring with the block on a groove in it. It gives us some dimensions, gives us some information in rotational inertia of the different pieces. And it asks us a couple questions. The first is to derive an expression for the spring constant of the spring. Well, I would start 3a. We'll go right back to our basics with 3a. F equals kx. I'm just going to worry about the magnitude, not the direction at the moment, so we're not going to worry about the negative sign there. We know it's a restoring force. So this implies that the spring constant is just going to be F over x, which implies then, well, x is equal to d over 2 in this case, and our force is mv squared over r. It's a centripetal force, a center-seeking force, which is m omega squared r, since we know v equals omega r. So we could write then that k is m omega squared r divided by d over 2 But r, our radius, is 2d. So this implies then that k is m omega squared times 2d times 2, all divided by d. Or simplifying this, we come up with the spring constant, k equal to 4m omega squared. Not too bad, mostly algebraic manipulation where we're pulling in a little bit of centripetal force, a little bit of work on springs, and a little bit of rotational motion, rotational kinematics. Now for B1, determine an expression for the rotational inertia of the block around the axis of the platform. Well, if we want to find the rotational inertia of the block, that's just going to be mr squared, which in this case is m times 2d squared, so that should be 4md squared. Again, just some rotational motion calculations there. Don't worry, we're going to up the level of difficulty in just a minute. B2, find an expression for the rotational inertia of the entire system about the axis of the platform. Well, the total rotational inertia, we just add up the individual rotations of inertia, moments of inertia. So we've got the moment of inertia of the block, plus the moment of inertia of the rod, plus the moment of the inertia of the platform, which is 4md squared, plus we've got mr d squared over 3, plus mp r squared over 2. And we've got some conversions here because we know mr is 3m, mp is 5m, and r is 2d. Let's write those down here. R is 2d, mr equals 3m, mp equals 5m. We'll justify our work here so that our total rotational inertia becomes 4md squared plus 3m d squared all over 3 plus 5m times 2d squared over 2, which implies then that our total moment of inertia, if we add all these up, works out to be 15 md squared. And that covers us for B2. Now C, find an expression for the angular momentum of the entire system about the axis of the platform. So, all right, for C, angular momentum is moment of inertia times angular velocity, which is just going to be 15 md squared omega. Seems straightforward enough. All right, moving on to part D. Derive an expression for the distance x that the spring is stretched when the rod reaches the position shown in figure 3 above. All right, let's go on to a new page here. So for D, I'd write that F, oops, I'm losing my page here. Let's fix that up. All right, so for D, we would write something like our force is equal to kx, which implies that mv squared over r equals kx, but we know that v equals omega r. We already found k is 4m omega squared, so this implies then that m omega squared r squared over r is going to be equal to, in our kx, we've got 4m omega squared x. We also know that r is d over 2 plus d over 2 plus x from our diagram, and r therefore is d plus x when I put those together. We can substitute in there to write m omega squared r equals 4 m omega squared x, which implies then that r is equal to 4x. But we just said r is d plus x. Therefore, we could write then that d plus x equals 4x, which implies then that d equals 3x, or to answer the question, x equals d over 3. All right, moving on then to part E. Assume the center of the rod is still moving toward the axis of the platform. Is the angular momentum of the entire system increasing, decreasing, or staying the same? All right, for part E, I would say that the moment of inertia is decreasing we know that omega is constant, maintaining the same angular velocity. Therefore, L, which is I omega, must also be decreasing. Pretty straightforward. And F. In order to keep the system rotating with constant angular speed omega, is the motor doing positive work, negative work, or no work on the rotating system? And justify your answer. Well, I would say we are doing negative work. W would increase without the motor as our angular momentum L decreases, so work must be being done on the motor. That makes it negative for that answer. And finally, part G. So all of these getting a little bit more into depth, but still nothing too terrible. G says, on the block in the diagram below, draw a single vector representing the direction of the acceleration of the block. Draw it so it's starting on and pointing away from the block. So you've got that diagram, and on that diagram, you've got your block, and you've got to draw the direction of the acceleration vector. Well, because it's moving in circular motion, there must be an acceleration toward the center of the circle. So there's a centripetal acceleration toward the center of the circle at that point. But we also know that it's slowing down. It's losing velocity, so there must be an acceleration, a tangential acceleration that way. Put those two together, and I would draw my arrow in that direction for the acceleration. And that concludes the APC 2016 Mechanics Free Response Exam. Hopefully that gave you some ideas of what they were looking for, and have a great day, everybody. Thanks for your time.